So another result which is quite different from the case of fundamental groups, which might surprise, and again easy to state and easy to prove. Okay, so now let's take a covering map here, P y y 0. So let P from y y 0 to x x 0 be a covering map. Okay, with fundamental groups we knew that the induced map is an inclusion, and more or less the converse is true, the whole Ricci-Galois theory, but here we have a different result. Okay, so let me take n is greater than or equal to 2. Theorem that we take P star from pi 1 of y y 0 to pi 1, sorry, not pi 1, pi n of x x 0 is an isomorphism. Yeah, so the fundamental group of a cover. This is actually a powerful way of calculating higher homotopy groups. Higher homotopy groups of cover are isomorphic. Because, for example, for the torus, and we'll use this kind of thing quite heavily, the universal cover is contractible. And if a space is contractible, we can see by a result that we had seen earlier, the homotopy type determines higher homotopy groups, that the fundamental group is higher homotopy groups are trivial. So they are for the torus as well. Okay, so that's very nice. So let's try and see the proof is that we construct an inverse. Verification that this is an inverse is a completely routine thing, so I won't do it. Okay, so however, I'm constructing this inverse. Okay, so we'll give it some name. Let's call it phi or something. From pi n of x x 0 to pi n of y y 0 as follows. Okay, so now suppose we have theta. So given theta, which maps 0 1 to the n. Remember, n is greater than or equal to 2. Boundary of 0 1 to the n to x x 0. Now this is simply connected. Okay, so by map lifting, yeah, so we have theta tilde, which maps 0 1 to the n to y. What do we know further? We know theta tilde of 0 0 0, the first base point, is going to be equal to y0. And what else do we know? Just because it's a lift, we know theta tilde of boundary of 0 1 to the n, the entire boundary, is contained in P inverse of x0. Okay, which is discrete. That's a key point. It's a covering space which is discrete. But this is connected. It's connected as n is greater than or equal to 2. This is what breaks down for the fundamental group. This boundary is connected of a disk if your disk is at least two-dimensional. And so if you have a connected subset in a discrete space, therefore theta tilde is constant. Oh, sorry, I don't mean all of theta tilde. Restricted to boundary of 0 1 to the n is constant. And we know what it is at one point. We chose it to map to y0. Therefore, theta tilde maps 0 1 to the n and relative to its boundary to y y 0. So in fact, I can define this as phi of. So more precisely, of course, I have to take a equivalence class. So define. This was a completely canonical construction. That's important. If we made choices, it's likely that some properties would break down. So completely canonical construction. There's a unique lift which will send the origin to the base point. And we define phi of theta to be the image of this unique lift. We proved, not up to homotopy or anything, on the nose, that theta tilde is going to be the kind of map that gives you an element in the homotopy group. So this is in pi n of y y 0. Okay. Now, since theta tilde is a lift, if I apply p to it, then you get back the theta. I mean the class of theta. So phi n of class of theta is this. Homotopy is lived, so this is well defined. So one-sided inverse came when we applied P. If you do it the other way, if you push down the map and then lift it up, well, by uniqueness of lifting, you'll see that the original map is actually theta tilde. So it's straightforward to verify these are inverses of each other. Hence you have a bijection. Hence this is an isomorphism between the fundamental groups. So again, this is very different from the fundamental group. But now we look at an example to slightly understand from the two things we have seen, that higher homotopy groups are abelian and their isomorphisms in covers. What happened to all the conjugacy in the fundamental group? It does appear. It appears in a kind of indirect way. We'll just give an example with a bunch of claims. We won't prove this. This is simply to understand something, but we'll have a precise definition there as well. Okay, so what we have is that, again, n is greater than or equal to 2. What we have is that pi n of xx0 is a module over the group ring. So it has an action of the fundamental group, xx0 module. So I want to relate it to the universal covers with an example, and then we'll look at the formal structure. And the relation between the fundamental group and covering spaces gives the tells you why the informal picture is the same as the formal one, except we have not formally computed any homotopy groups. So one thing will have to be taken on faith. Okay, so this is S2 and this is S1. So we have a x is going to be the so this is going to be S2 wedge S1. Okay, so pi 2 of x with some base point x0 is isomorphic to pi 2 of the universal cover of x tilde with some inverse image base point. Okay, and what is this space? Well, we expand the circle and we get a whole bunch of spheres. Now, as I said, you have to think of homotopy groups as maps from spheres. We don't know that these are all distinct maps and they're non-trivial, etc. The easiest way to prove that is probably Hurewicz theorem, which will require homology. But nevertheless, you can imagine that these are all different elements. Now, deck transformations act on them and take one to the other. So pi 2 is going to be not just one sphere, but a whole bunch of spheres like this. The formal construction is actually even easier than this description. Namely, the action is the following. If I have given whatever I'll call it f like this, and alpha, maybe for consistency I'll call it alpha like this, which is a path. Okay, alpha acting on f is going to be the following. Remember, alpha is a loop, so this guy goes to x0, this guy goes to x0. Okay, so I keep f kind of small inside, and this time instead of taking a radial homotopy in each radial direction, I put alpha. It's not that difficult to write a formula for this. You have a smaller square inside a bigger square, and you have alphas which start here and go back by alpha. So this is the action. If you see, if you have alpha and beta star alpha acting, that is the same as alpha acting and then beta acting. That is, you do have a group action and all the properties are nice. It's quite easy to see. So what I want to point out here is that you do have the non-abelian structure not internally. In the fundamental group, you have it internally by the conjugation, but instead externally, you have a group ring structure with a non-abelian group acting on this abelian group. And this gives you a nice and quite useful structure as well. Not in this course, we won't see anything further here. Here we'll move towards trying to understand how homotopy groups control homotopy type in the case of CW complexes, to a small extent in the case of arbitrary spaces as well.